So today's talk is going to be some sort of tutorial on what kind of signature schemes we have encountered on the blockchain space. And by no means this is not going to be exhaustive. I'm not going to cover every single thing that we have seen in terms of digital signatures, but I'll try to give like a pretty fair overview. So let me start and say, why do we care about digital signatures and what are digital signatures? So I'm going to use the cryptographic definition of a digital signature scheme. So if you ever took a cryptography class, you have seen this definition. So typically we define a digital signature as a protocol that consists of three algorithms. There is a key generator algorithm that takes as input some security parameters and outputs a pair of a secret key and a public key. There is a signing algorithm that takes as input a message and the secret key and outputs a signature. And then there is a verification algorithm that takes as input the message, the public key and the signature. And if the signature verifies for that particular message under that particular public key, the verification algorithm will say accept, otherwise it will say reject. So the idea is that the verification algorithm can be run by any third party as long as it knows the public key of the sign. The two crucial security properties when we talk about signature schemes are correctness, which basically means that if a signature was signed with a secret key that corresponds to a public key, it should also verify under that particular public key. And enforceability, which informally says that if you don't own the secret key, if you don't know the secret key, you shouldn't be able to produce accepting signatures under the corresponding public key. And I'm going to formalize this definition soon. So why do we care about digital signatures in Web3? Because they're literally everywhere. Every single blockchain system uses digital signatures at one point or another. The main reason that we use digital signatures for is to authenticate transactions. And if you just recall for a second how Bitcoin transactions work, that they have inputs and outputs. Basically, in every single Bitcoin transaction, you need a signature for every single input in the transaction, okay, in order to verify the transaction. So beyond that, beyond like the basic use of digital signatures, we've seen many more exotic, as I want to call, digital signature schemes that appeared in the blockchain space. We have schemes like multi-signatures, threshold signatures, ring signatures, adapter signatures, and we also care a lot about certain properties or features of digital signatures like malleability and aggregation. So what I'm going to do in the rest of the talk is to cover the three most popular digital signature schemes that we have seen in the space of Web3, discuss the properties of aggregation and malleability, and then also overview at least the properties of these like more exotic, as I call, signature schemes like multi-signatures, threshold, and so on. And feel free to stop me at any point or ask questions whenever you have. So I'm going to start with ECDSA because this is the signature scheme that is used by Bitcoin and many, many more systems. It was introduced back in '92 by Scott Vanstone. And probably some of the reasons for which ECDSA was adopted by Bitcoin from the very beginning is that it is a standardized scheme, it is efficient, it is LUT curve based, and it's not patented. Okay, so it was freely available to use. So I'm going to give you a description of how ECDSA works. And for all these schemes, I didn't clearly define that when I gave you the algorithm from which the signature scheme consists of. But for many of these signature schemes, there is also some sort of setup phase that certain parameters are decided. So for the ECDSA signature scheme, we need an LUT curve. Specifically, Bitcoin uses SecP 256K1. We need a base point in the curve, the point Z. And we also care about n, which is the order of the point Z. In order to generate your secret and public key, you start by picking the secret key as a random integer in the space from 1 to n minus 1. And then you do one point multiplication between the secret key and the base point G to get your public key. In order to sign a message, you start by taking the hash of your message, and then, crucially, you pick a random nonce that I'm going to call K, and compute the elliptic curve point that is defined by this random nonce K. So you're going to do again a point multiplication with G and get the coordinates x1 and y1. You're going to isolate x1 and take it modulo n. And then, for your signature, you're going to inverse your random nonce K, and then take the hash plus the secret key times the randomness that was generated by K modulo n. Yes?
What is the second key?
So this is the particular elliptic curve that is being used by Bitcoin. So there are many, many different options on elliptic curves that one can use in such schemes, and this is the specific one that is used by Bitcoin. So what you output as your signature are those two values, R and S. How do you verify the signature? And I'm not going to really show you correctness here. I'm not really going to show you why things work out, but just to have an idea of what kind of computations are happening here. So basically, again, when you verify the signature, you need the message, the public key, and the signature consists of those two values, R and S. You have to check that that's a typo, that R and S are in the correct space. You recompute the hash of the message, E, and then you inverse S, take S to the -1, and you compute two values, E times S minus 1 and R times S minus 1. And then you do 2 point multiplications with both U1 and U2 to get an elliptic curve point x1, y1. And you're going to output that your signature is valid if the R that was given as part of the signature is equal to x1. And again, I'm not going to show you correctness here because I would have to dig into a little bit on how this point multiplication works and why there is like a symmetry here, but you have to trust me that indeed, if the signature was correctly computed, R is going to be equal to x1 here. Okay? For other signature schemes that we're going to see down the path, it's going to be much easier to actually verify correctness yourselves. What I want to highlight here a little bit is a few important points. In terms of security, and again, I'm going to formalize things a little bit more, the security of ECDSA actually relies on the hardness of the discrete logarithm problem in elliptic curves. So if you see the public key, it's hard to extract the secret key here. And one more point that I want to make here is that the way that I defined ECDSA here is deterministic. What does this mean? This means that if I'm signing the same message with the same secret key, and every single time I pick a different random nonce K, I'm going to produce a different signature. There is a way to actually make ECDSA deterministic, and you can refer to a particular RFC if you want to see the specification for that. In a very high level, the idea is that you're basically not just picking K randomly, but you are hashing the message together with a key in order to fix a particular value for that message and key. But you can refer to the specification for more on that. So in terms of efficiency, this might seem like a lot of operations, but many of these are actually pretty cheap. The operations that we actually care about, the most expensive operations in this scheme, are actually the point multiplications. And as you notice, during signing, there is a single point multiplication. And what I also want to highlight here is that at least for the non-deterministic case, you can actually pre-generate these K and R values, because you can see that up to here I'm not really, using the message. The message E is only used at this part. So this operation and this operation could potentially be pre-computed. So you can kind of save a little bit on the signing phase. During verification, you have to do 2 point multiplications, and there are also some tricks there with like pre-compute tables and something that's called the Samir's trick that could break this down to roughly 1 point multiplication. There is one more operation here that is kind of expensive, not as expensive as the point multiplication, and this is the inversion of the value S. But these are the most expensive operations here. In terms of sizes, the signature size is 64 bytes, and the key sizes are 32 bytes. Technically, for Bitcoin, the size of signatures are a little bit larger, roughly between 71 to 73 bytes, and that's because ECDSA was implemented with the OpenSSL library and has a particular encoding that the signatures need to satisfy, which kind of blows up the size a little bit. Okay, so the size of signatures on Bitcoin, I think most of them actually these days are 71 bytes. All right, so, any questions on how the scheme works, high level here? I bet most of you have actually seen ECDSA before.
Any like full node implementations actually compress the signatures on?
I was actually looking into this and I'm not aware. Yeah, that's a good question.
10% savings.
Exactly, yeah, because if you bring this down to 64, that's actually important. So, yes?
What is the Schnorr trick?
So basically it's a combination of pre-computations that you can do on certain points in the curve and inversions that you can do a little bit faster. It's hard to describe it, but I can give you references if you want to look at it. Yeah. And my understanding is that actually certain full nodes are using such tricks to verify signatures a little bit faster.
So it's like for a specific generator point, you can get much faster conversions, or like what's the?
Yes.
Okay. Yeah.
Yes. Again, with certain pre-computation tables.
Okay.
Moving on into security, as I said, the critical properties for digital signatures are correctness, which is easy to describe, and also unforgeability, which I will now describe a bit more formally because this kind of actually matters a lot for security. So, usually in cryptography, we define security via a security game. So we're trying to capture exactly what an adversary can and cannot do with a security game. So here the idea is the following. We define a challenger and we have an adversary that tries to break the enforceability of a scheme. The challenger typically will pick a pair of a secret key and a public key, will send the public key to the adversary, and then the adversary will start the so-called challenge phase, where it's going to select messages and send them to the challenger. The challenger will sign the messages with that particular secret key and send back signatures to the adversary. And this can be repeated many times, technically a polynomial number of times. And at the end of this game, the adversary is going to output its forgery, this n star and sigma star. And we're going to say that the adversary wins. The adversary, in other words, breaks the enforceability of the signature scheme if it manages to output a signature that verifies and the message n star wasn't queried before. Okay? So this is what we call unforgeability. And we call this existential chosen methods attack unforgeability. So having this definition, when we're trying to prove security of digital signatures or of any cryptographic scheme really, what we're trying to, the ideal theorem that we want to give is that the signature scheme XY is unforgeable under a particular hard problem in the standard model. So this is like the ideal security definition that we want to give. So what is the case with ECDSA? We know, like, there has been a lot of research in trying to actually formalize and pinpoint exactly what is the level of security of ECDSA starting back in 2002. So back in 2002, Brown proved security of ECDSA in the so-called generic group model, which is kind of an idealized security model. It's not like a standard model, under hash collision resistance. Later in 2016, we had security again in GGM under different hash assumptions and an idealized function that was used for like the mapping of the random nums and the elliptic points. And very, very recently, a couple of months ago, we had a new proof of security by Groth and Soup on a special version of the generic group model that was specific to elliptic curves. So, for those of you who are not cryptographers in the room, this might sound kind of, funky and really wondering what are the differences between these results. Well, in practicing as cryptographers, we really care about the underlying assumptions, the models under which signature schemes are being proven under. And the problem with ECDSA is that all these systems under which these security proofs are given are actually kind of idealized models of computation. So again, these are not like standard model proofs. Again, this doesn't mean that these are insecure or there are certain attacks. It's just not the ideal type of security proofs that we'd like to have. Okay? Just to clarify that again, there are no attacks. I'm not claiming any attack. It's just that we don't have proof of security for ECDSA that are under the most acceptable standard models. Okay? Beyond the theoretical security, and as I said, there has been a lot of effort on that, ECDSA is actually pretty, implementing ECDSA is actually pretty notorious, and there can be many issues that completely happen at implementation level, or incorrect configuration of APIs and so on. And I just want to highlight a couple of attacks. So there is a well-known attack that allows an adversary to recover the secret key from a signature if this random nonce k that was used during signing was revealed. So if for any reason this randomness k that you picked during signing was revealed, then an attacker can extract your secret key. And to make things even worse, this can actually happen even with like parts of k being public, or even by having a way to have like a biased randomness generator that spits out this case, and you can figure out something about the next randomness that's going to be picked. So these are harder attacks. They use like Fourier analysis, lattice-based attacks, and there is like a plethora of research work on that as well. So the good practice there is to actually keep all keys used secret, do not reuse, and be very careful with randomness sampling.
Do any of the wallets generate them like pseudo-randomly using a PRF, or are they all?
I don't know. It's a good question.
I think a Bitcoin is pseudo-random. Like, the sec key is like very much designed to not use randomness, because then you might have a bad randomness generator, and then you get random these issues. So the better way is to just generate it, as Joe was saying, from your private key, pseudo-random.
Also, the question, if you don't know the bias, but like there exists some bias, can you still like attack it?
I don't think so. I think they actually need to know, certain patterns on the next nonces that are going to be selected. The second point that I want to make about ECDSA is that ECDSA signatures are malleable. Okay. And what does this mean? Specifically for ECDSA, it's actually pretty easy to see why this happens. Because the elliptic curves used, they have some sort of symmetric properties. It's very easy for an adversary looking at the message and the signature to just take the symmetric point of the signature on the curve and come up with a second signature that is also valid for the same message. So this can create replay attacks, especially if signatures are used as the unique transaction IDs of transactions in Bitcoin, and this was a case with Mt. Gox many years ago. And what is important to enforce here is that there is a single canonical signature for any given public key enhanced message, and this is something that is actually adopted by Ethereum. So they kind of, remember that I said that it's very easy in ECDSA to just take like the symmetric of your signature and have like the minus sigma also being a valid signature. So what Ethereum does is that it kind of splits the space in half to essentially not allow you to be able to pick this symmetric point.
Are you going to talk about the Mt. Gox attack?
No, not in details. No. Another thing that you can do here, specifically if you care about these unique transaction IDs, is as Bitcoin does, to basically treat the transaction IDs differently with the SegWit introduction. And again, I'm not going to get into too many details on this because there is so much to cover. So this kind of concludes my discussion on ECDSA, and what I'm going to do now is to actually move into different signature schemes and see what else is out there. Any more questions on ECDSA? And again, I'm happy to give you references. There is a lot going on there. So what do we have beyond ECDSA? There are basically two more types of signatures that we've seen a lot in the blockchain space. The first type of signatures is the so-called Schnorr signatures, which are now accepted in Bitcoin post-Taproot and Polkadot. And there are also the ECDSA signatures, which are basically the deterministic Schnorr signatures. And we also have BLS signatures, which are adopted by Celo and hopefully Ethereum too. So I will basically go over Schnorr and BLS signatures and then move on with the other more like different features and properties of signatures. So before doing that, why do we care about different signature schemes? We care about more efficient signature schemes. We care about schemes that have better or more standard proofs of security. And we also want extra features, as I'm going to discuss, which were not supported by ECDSA. So Schnorr signatures are actually kind of older compared to ECDSA. The problem, though, is that Schnorr signatures were patented up until 2008, so many people actually believe that this was the reason that they were not immediately selected by Bitcoin. They are not standardized yet, as far as I know. There is a specific specification for Bitcoin for the particular elliptic curve that is used in Bitcoin, and let me show you how they work. So the parameters that we need for the scheme is a group G of prime order Q with a generator LG. You want this group to be selected in a way such that the discrete logarithm problem is hard. So now I'm going to show you the scheme not by using elliptic curve notation, but by using point multiplication to kind of make it a little bit easier to distill. So the key generation algorithm picks a random secret key, computes the public key by taking the generator and raising it to the secret key. Again, because of the discrete logarithm problem, it's hard to figure out the secret key from the public key. And now the signing algorithm again picks this random nonce k. It sets R to be Z to the k, hashes the message along with this randomness R, and computes S to be k plus E, which was the output of the hash, times Sk, the secret key, mod Q, and the outputs are nice.
Should probably include the public key as well, no?
What's that?
The public key in the hash. Otherwise, you could...
Good point. Yes, you need to include the public key in the hash. Yes. So to verify, it's actually easier to see why the signature verifies. You need to recompute E, and here, if you obviously include the public key, you have to include it here as well. And verification is pretty simple. You just take the generator raised to S, and if you see S is this K times E secret key, so this is Z to the K, Z to the E times this K, and that's R, which is again Z to the K, so the two Z to the K's go away, public key raised to the E, and again if you see Z to the E times this K, you can see that things actually cancel out and this verifies. It's much easier to see that it verifies compared to ECDSA. So in terms of efficiency, things kind of look similar to ECDSA. We have one exponentiation that is needed during signing and two exponentiations that are needed during verify. You can think of exponentiations being almost equivalent to point multiplications here. So efficiency looks pretty similar. And the signature size is actually 64 bits. And again, the keys as before are 32 bytes, 64 bytes, and signature keys are 32 bytes. similar to ECDSA for the same security level. Okay? So what do we know about security for Schnorr? So Schnorr actually has a better unforgeability property, has a better unforgeability definition. So recall the unforgeability definition that I gave you before. I was saying that the adversary wins if it outputs a message and a signature such that the message was not queried before. So now I'm allowing the adversary to win even if it outputs a new signature on a message that it did query before. Okay, so basically again, if an adversary manages for a message that it has already queried to output a different signature than the one that it received during the challenge phase, this is still considered an attack. So we still consider this adversary to be breaking the scheme. Okay? And this is a stronger property, this is a better property than the one that is satisfied by ECDSA. And this is basically the reason why the Schnorr signature scheme is not malleable. Okay? It doesn't allow to have multiple signatures for the same message. So what do we know? What are the theoretical results that we know on the security of Schnorr signature? So there is this very celebrated and famous result by Pansevall and Stern in '96, who formally proved Schnorr signature scheme in the random oracle model under the discrete logarithm assumption. So they introduced a technique, a proof technique that is called the forking lemma, and it's a proof technique that is used in many security proofs of signature schemes. They gave a loose reduction. Again, I want to highlight that the random oracle model, similar to the generic group model that was used in ECDSA, is again like an idealized model of commutation. It's not a standard model, but it's probably a little bit more standard compared to GGM. And there was again like numerous results, and I'm not being exhaustive here, that actually improved the tightness of the reduction that was originally given in '96. So I just want to mention that just because it popped up like a couple of days ago, and many of you might have seen that on Twitter. So as I said before, ECDSA is the deterministic version of Schnorr, and I just want to highlight like an implementation pitfall that was actually discussed on Twitter by Kostas Halkias, one of the SUI Mysten Labs cryptographers. So basically, they found out that roughly 40 ECDSA libraries for the particular ED 25519 curve, they would expose the private key if the signing function was misused, either accidentally or on purpose. And what was the problem there? So basically, the problem there was with the signing API of the library. So the signing API essentially embedded the secret key, but allowed to give as input the public key as well on top of the message. So this could potentially give rise to an attack such that an adversary could extract the embedded secret key if it asked for signatures on the same message under two different public keys. And again, it's a little bit hard to show you like the math behind the attack, but it's actually not that, nothing fancy. It's not like an expensive attack or something. So the reason that I wanted to mention that again, as I said, it's because it just popped up like a couple of days ago, and it received a lot of attention on Twitter. And it's a very clear example of how things can go wrong completely in an implementation level. Okay, so no, there were no known, at least, vulnerabilities that could actually, be an attack vector, but many companies that were using these libraries, they're trying to patch things up. Okay. So a very nice property of the Schnorr signature scheme, and here I'm just recalling the Schnorr signature for you, is what is called batch verification. And this is a property that is not supported by ECDSA. So what batch verification allows to do is the following. So assume that you have a miner, And it looks at a block that has a whole bunch of signatures, and of course, the miner should verify all signatures first. So the nice thing with Schnorr is that you can actually reduce the cost for the verification of the signature. So basically what do you do is that you take all the signatures and look again, this was the expensive verification operation that required 2 exponentiations. So you would have to do 2 exponentiations times n to verify all the signatures individually. But because of some essentially linear properties that Schnorr satisfies, you can take the sum of all the s's, raise g to the sum, which is like 1 exponentiation now, and then multiply all r's together, and then do, of course, the separate exponentiations for every public key. So the nice property here is that you're taking this from 2 times n exponentiations to n plus 1. Okay, so this is a significant improvement on the time of verification here. I'm trying to draw some comparisons between ECDSA and Schnorr, and I'm also going to add BLS in the picture. So again, specifically for the case of Bitcoin, ECDSA signatures are larger. Signing verification cost is pretty similar. In terms of security, Schnorr has stronger security and it doesn't support malleability, and it's also proven secure in a kind of more acceptable security model. And it also has this very nice feature of batch verification that is missing from ECDSA. So next I'm going to move into BLS. Are there any more questions on ECDSA and Schnorr before doing that?
GGM model contained inside the RO model, or
Sorry, can you repeat that? Is
the GGM model contained inside the RO model?
No, so these are 2 very different computational models, and in general, the GGM model is considered more strong compared to the random oracle model, and in cryptography, when we say something, when we say the model is stronger, it's kind of worse than the random oracle model. Yes?
For the batch verification, you just showed it like as an adding. Do I not need to take a random linear combination?
Yes, it does.
Okay.
I mean, I'm just showing the basic. Yeah, yes, of course, yes. I'm just showing the basics.
So, just, to summarize, there's basically no reason to use ECDSA ever.
I wouldn't like to make such, to come to such conclusions, but
No known advantage besides patents or like standard implementations.
I think they expired.
Yeah, the patents.
the patent expired in 2008, the Schnorr patent. But at least by
It's kind of
browsing online, because it was so much on the edge, people say that this was the reason that it was not.
Yeah.
And also it was not standardized back then. Even now, Schnorr, as far as I know, is not standardized. As I said, there is this specification for Bitcoin, but there is no general standard.
I guess the great irony is the patent was it expired just in time
Right.
that Bitcoin could have used it, but
Right.
it's a lot less widely used at the time.
Right. I mean, again, this is just speculation of why it wasn't used, and we cannot be sure. All right, so let me move into BLS, which is going to be the last scheme to cover. So BLS signatures are much more modern, I guess, compared to ECDSA and Schnorr, introduced by Dan Bonnet, Ben Lin, and Hovav Savon in 2004. There is a standardization effort in progress right now, and they use a different primitive instead of just like the basic discrete log that Schnorr and ECDSA was using. They use something that is called the bilinear pairing, and they rely on elliptic curves that are actually pairing friendly. And what I want to highlight here is that the particular elliptic curve that is used by Bitcoin does not satisfy this property. Okay, so we could not implement BLS on top of Bitcoin, say. So I just need to give you this very short prelim here on what the bilinear pairing is, and then after you understand that, you're going to see that the scheme itself, it's actually very, very straightforward and very easy to digest. So a bilinear pairing is basically a mapping where that takes two inputs from Z, where Z is a pairing-friendly curve, and gives an output to another curve. The very, very nice property that you have here is that if you have two values, G to the A and Z to the B, that are parts of Z, then if you take the pairing, if you apply the function in G to the A and Z to the B, then this is equal to basically bringing the exponents outside and taking e to the g comma g raised to a times b. And as you're going to see, this property is going to make our life very, very easy in verification. So let's see how the scheme works. Again, parameters, group G of prime order Q with generator G. Again, you want the discrete log to be hard. The public key and the secret key are selected in exactly the same way as with Schnorr signatures, but now hashing is done differently. So the signature is just one line. Remember ECDSA and Schnorr before that had multiple computations to reach the signature. So you basically just hash the message and you raise the secret key. So notice that this hash function needs to have kind of special properties. It needs to be a hash function that maps to points in the curve. So not every single hash function can be used here. And then to verify that the signature is correct, and sorry, this should just be sigma here, you just need to check if the pairing of sigma comma z is equal to the hash of the message comma public key. And here again, it's very, very easy to see why the algebra works. Verification is very nice. Do people see why this verifies? It's much simpler than before. So something that I want to highlight about BLS signatures is that they are deterministic. There is no randomness peak here. And on top of this, they are also unique. So unique means a different thing than deterministic for digital signatures. So unique basically says that there is no other signature, so that every signature really maps to a particular message and secret key, and that's unique. It's not possible to compute another signature sigma for a different combination of message and secret key. Okay, while deterministic says that for this particular secret key and message, there is a unique signature. Okay, but again, unique the other way is that there is no other combination of message and secret key that would give you the same sigma. Okay, so it's kind of, those two properties, I feel that they're often confused. All right, so again, what happens in terms of efficiency? So we had one exponentiation for the key generation, similar to all the previous schemes, and one exponentiation for signing. And for the verification, what we need is to compute two pairings. So typically, this pairing computation is more expensive than the exponentiation computation, so this is something that we have to keep in mind when we're looking into BLS. So verification can be more expensive. Signature size is much smaller, it's like half compared to Schnorr and ECDSA, because it's just one group element, so it's just 32, 33 bits and bytes, and signature sizes are also 32 bytes.
So wait, what's the size, 96 bytes?
Sorry, I was just counting public key, secret key. Sorry, I should have erased that. I was just signature size plus public key plus secret key, but it's ignored. So what do we know in terms of security? The security of BLS has the same, so BLS satisfies the same unforgeability definition as with Schnorr. It has a stronger version of unforgeability. And in terms of theoretical results, the original paper showed that BLS is secure in the random oracle under the so-called computational Diffie-Hellman assumption. And then there was a more recent result that actually managed to make this reduction a little bit tighter in a new model in a new security model that's called the algebraic group model under the discrete log assumption. So again, if I try to put together and draw some comparisons here, the main advantage of BLS signatures is that they're much shorter. Signature verification cost, signing cost is about the same. Verification cost is higher because, as I said, like the pairing operation is typically more expensive than exponentiations. The security is comparable to that of Schnorr, and it also allows for batch verification.
So, I mean, do people worry about, like, you can only implement BLS in pairing-friendly curves, so there's more chance of some discrete log break because the curves have extra.
Yeah, I think they do. Yeah.
Yeah.
So there's a lot of discussion on the right curves, and so BLS though has many other nice properties that make it attractive, and I want to highlight some of them. Does the seminar go up until? Is it 1 hour or 1 hour and a half? Okay, so right, okay, and we started a bit late, so okay. So right. So a nice property of BLS signatures is that they also allow for aggregation. And let me explain what this means by giving you kind of the definition, explaining what an aggregatable signature is. So when I defined digital signatures before, I said that they consist of 3 algorithms: key, gem, sign, verify. An aggregatable signature scheme will add 2 additional algorithms: the signature aggregation, that is going to take as input a vector of messages, a vector of keys, and a vector of signatures, and output a combined aggregated signature, and a verification algorithm for this aggregated signature. So if we kind of try to view that as a graph, the idea is that we have an algorithm that takes signatures under different public keys and on distinct messages, and combines them to a smaller, to a much shorter aggregated signature. So let me show you how this is possible to do with BLS. And obviously, the main advantage that makes this property very sexy on the blockchain space is that it can really compact the space, the storage space in a block. Instead of storing every single signature, you can just aggregate them together and, you know, really reduce the storage space there. So again, remember how the BLS signature works. I'm just recalling the scheme up there, and let me show you how can you possibly combine multiple signatures together. The idea is pretty simple. You just take all the signatures, again, think different signatures, different messages, different public keys. You multiply all the signatures together, and then in order to verify, which in a sense also supports batch verification at the same time, in order to verify, you just take the pairing of the aggregated signature, and then you multiply the pairings of every single message with the corresponding public key. And if you do the math and you bring out the exponents here, you're going to see that this actually verifies it. So again, the nice property here is that instead of storing n times 32 bytes for the signatures on the chain, you're now only storing 32 bytes instead. Still, again, you would have to store separately the public keys and the messages because they're different. You can just compact the signature size together. You can just like compact the signatures together. Okay? And as I said, this naturally gives you batch verification, and it takes the pairings from 2 times n to n plus 1. Okay? Is it clear why this works in BLS? Yep. So this is a very, very nice property. So a different property that is also very commonly discussed in the blockchain space is that of multi-signatures. And if you think about what multi-signatures are, you can think of them as a special type of aggregate signatures. But now the difference is that you want to produce a single signature, but on the same message. Again, remember that in aggregate signatures, you had different public keys, different messages. Now you want to have like a bunch of signers sign together the same message. Such schemes are possibly interactive, but not always. And essentially the idea is that instead of having this like single sign algorithm, you might have an interactive algorithm that is run among every signer in order to produce the final signature signal. When you verify the signature, you still need to know all the public keys that were involved in the sign. Okay, again, the main difference is that you have a single message. So what do we know? Well, first, why do we care about multi-signatures on web3 and blockchain systems? They're very, very valuable in multi-user wallets, where you want to have multiple users signing a transaction in order to go through. But we've also seen them being heavily used in layer 2 protocols, like certain Bitcoin tumblers, and also on payment channels like the Lightning Network. So let's see how we can build BLS multi-signatures. Again, I'm just up here just recalling how BLS works. And now let's think that, I'm doing the same operation that I was doing before as with aggregated signatures, but now again, keep in mind that all the signatures now correspond to the same message. So basically what I'm doing is that I'm multiplying all the signatures together, and now verification looks even simpler because on that side I'm still taking the same pairing as before. Actually, I forgot to change the subscript here, that should be the multi-signature. And I can only do, luckily, 2 pairings here by just multiplying all the public keys together and taking the hash of the message, because there's a single message here. So this would very nicely give you a multi-signature scheme if it worked, but unfortunately this is vulnerable. It is vulnerable under a special type of attacks that are called the wrong public key attacks. And basically, if you did BLS multi-signatures this way, it would allow an attacker to create an adversarial public key, which I'm calling the public key star, using an honest user public key, and then kind of frame this user, the honest user, as also signing the message, although the user never signed the message himself. So the idea is that if an attacker just knows the public key of a user, can set its own public key to be as pk star z2 sk over the public key of the user, where sk is actually should be sk star, the secret key of the attacker, sign this way with just its own secret key, but then the signature will verify under both pk and pk star. So it will look like also the honest user signed this signature. Okay? So this is actually a problem. We wouldn't like to be able to do that. And now I want to ask you guys, do you actually want to see how BLS solves this problem? Do you want to see the scheme, or just take it as granted that there is a way to resolve this issue of BLS and move on? Yeah? Okay. So I'm going to take this slide. And I'm just using the slide actually by the author. So this optimization, this extra feature on BLS signatures was not added with their introduction, but it was added in a paper called Compact Multi-Signatures for the Blockchain that was published in 2018. And the idea here is the following. So again, key generation as before. I mean, here they're using different, like a little bit of different notation for the generators. But now here is how do you aggregate the signature. You need to start by first aggregating the public keys. So what you do is that you take all the public keys of the signers of your message and you multiply them together after raising them to this value alpha, which is computed by taking the hash function on the concatenation of the public key that you are multiplying and all the rest of the public keys. Okay, so again, it's going to give you a different alpha for every public key because you're changing the order of the input. So then, after you have this like aggregated key, in order to sign, you first compute all the separate signatures, all the sigma i's, and then you also aggregate them together in the same way you did for the public key. So you take all the signatures, and every corresponding signature you raise it to the corresponding value alpha, which is again the hash of your own public key and all the rest of the public keys. To verify, You just need two pairings. You take the signature and Z2 on the one side, as you always do with BLS. And here you just has the message and you take the aggregated public key. So this result was actually proposed in some forum post by Maxwell, I believe, and then, as I said, was formalized later. And this gives secure multi-signatures, BLS multi-signatures, under some flavor of the CDH problem in the randomorphism.
So is PKI also included in the set of, or the concatenation on the right side? No.
I think it does, yes.
It is.
Yes.
Okay.
But again, the important point to notice here is that this AI is going to be different for every key because you're putting that particular public key first. And again, literally you can think of this whole thing as a concatenation for some reason.
And are G1 and G2 required to be the same in the setup, or is it more general?
They're different. In the previous slide, I was showing this as being the same for simplicity, but in practice they're different.
Does that affect any copies?
Nah, it's just it was mostly done for notation, to simplify notation.
So is it important that H1 and H0 are different hash functions?
Yes, they are different hash functions. The crucial part with this hash function, with this particular hash function here that is used in signing of BLS, is that it is a special hash function that maps to elliptical points. And this is important, and not every hash function satisfies that. This is a regular hash function that just maps to an elliptical here, so there's more flexibility. And again, in implementations of BLS, there is quite some discussion, and I believe there are also some relevant research papers on this, like hash to elliptical points functions, which might also give some complications. So obviously, like a point in the implementation of BLS that kind of needs a little bit of special treatment. So, in terms of security, again, the enforceability gain changes when we refer to multi-signatures. It's not the same as before. So here the idea is that, again, you have an adversary, takes as input a public key. This is like the honest user's public key, that the adversary doesn't know the secret key. Because this is a multi-signature scheme, we might ask the adversary again. The adversary might ask the challenger to receive a bunch of signatures under the corresponding secret key. But also the adversary might create a bunch of secret key pairs, secret public key pairs on its own. And we're going to say that the adversary breaks unforgeability if it manages to output this like multi-signature on this like combined public key that also includes the honest user's public key on a message for which it didn't receive a signature up here. So we're basically saying that it managed to create a multi-signature that includes, on this particular message, that includes a signature from the honest user as well, although the honest user never signed it. Okay? So again, it's like a different flavor. We have to be very, very careful on how we define these things. Again, I'm putting certain things under the rug here, but these definitions can be even more complicated. They might allow the adversary to be like adaptive, to, for example, declare ahead of time what are the keys that it has generated and they're considered to be corrupted, or be able to corrupt users and generate more keys as as the game keeps going. So there are many, many different flavors of these definitions. So just giving you the very basic one. So what do we know about multi-signatures? For the BLS, we already saw the result. The nice thing about the BLS multi-signature is that, as we saw before, it kind of looks like an aggregated signature. It doesn't really need interaction between the signers. Multi-signatures are also supported by Schnorr, so it's not a feature that is missing from Schnorr. But Schnorr multi-signatures require interaction in order to produce the signature. They cannot just be done by kind of aggregating things together. A naive protocol is easy to see without interaction actually, but again would be insecure under this a similar key attack. Again, there has been a long line of research on Schnorr multi-signatures, giving you only like the most notable results. There was an impossibility result at some point on 2-round Schnorr-style multi-signatures. And more recently, there was a paper that actually managed to overcome this interaction by changing a little bit how the signing process would work. And this is the so-called MUSIC2 scheme, for those of you that have heard it. And the nice property about those multi-signatures in Schnorr is that the final signature is actually indistinguishable from a regular Schnorr signature. So you cannot even tell if a signature is a multi-signature or not. ECDSA also supports naive multi-signatures in the sense that it can just concatenate things together, but without all these nice savings in the size of the signature or in the verification process. So this is what we know in terms of multi-signatures. Again, the main point here is that for Schnorr, you need interaction. Okay? So I want to cover a few more signature notions, not in as many details as BLS. So I'm not going to be showing you how schemes work. I'll just tell you the definitions and I'll try to highlight the differences between the different properties that the signature schemes have. So the next signature I want to mention is the so-called threshold signatures. So multi-signatures have this n out of n signing policy. You want to have all n signers signing the message. What if we have other policies? What if we want just to get these signatures out of a set of n public keys, and so on. So threshold signatures allow us to do that, and they have an important caveat though, an important point that we will be careful about. So the key generation process is not independent as before. It's not the case that every user can just generate their own keys. Typically in threshold signatures, you should think of the, actually let me state it the other way around. In multi-signatures, you should think that every user has its own keys and they can put their keys together to sign something. In threshold signatures, you should think of it as a group of signers has a key and they break down this key in pieces and give all the pieces, all the shares of the key across the different members of the group. That's why the key generation process in aggregate signatures is actually a multi-party protocol. It's a protocol between the participants of the group, between all the n parties, in order to define a single public key that looks like a regular signing public key and all the shares of the secret keys. So you might have heard this as being called the distributed key generation protocol. There is a lot of research on just this part of the protocol, like leaving the threshold signing aside, just like how can we efficiently create those keys. And I think Sarah also has some recent work on DKG. And then the signing protocol is also typically interactive. So we want all the signers to interact together using their shares of the keys. Again, the nice part is that you can only have like 3 of the signers sign a key. The signature will verify as long as the correct threshold of signatures was satisfied.
Do you rely on a secret channel for the setup of that, like between the participants?
Yeah, you usually want the RFA authenticated.
Okay. So like you couldn't just post like the interactions to like the public chain and then work from there?
Not as far as I know. If you know of any result that actually allows authenticated channels, indicates it. I'm not aware of any.
Okay.
So what are the nice things? As I said before, the signature is completely indistinguishable from a regular signature, the same for the public key. And the nice property of threshold signatures is that you actually get privacy for the signers. So you don't really know who are the T signers out of the N that actually signed the message. The problems are this interactive, expensive, one-time key generation. It's hard to update the public key. So let's say that you want to remove a member from the group or add a new member to the group. You have to recreate new keys. And also the signing is necessarily interactive, while, as I said before, for BLS, for example, in multi-signatures, there was no interaction. So if you try to compare threshold signatures and multi-signatures, it's really a trade-off. It depends on what kind of applications you want, what kind of features you want. The most important thing is that, in terms of sizes, typically threshold signatures are shorter. You just need a single public key. Multi-signatures, eventually you need all the public keys. The key setup is required in threshold signatures. In multi-signatures, it's completely transparent, everyone does its own. Interaction is needed in threshold signatures, not always for multi-signatures. And signer privacy is threshold signatures hide who signed the methods. Multi-signatures, on the other hand, offer accountability in the sense that, so the privacy thing can be a feature or a problem depending on what is your goal. Yes.
Are there impossibility results on like a non-interactive?
I'll get to some impossibility results for threshold.
Is the resulting signature and the threshold signature the same no matter which key signers you have, or the signature might be different depending on?
The signature might be different, but still it doesn't allow you to distinguish. Like the signature, itself can be different, but you cannot distinguish that.
On the previous slide, when you were doing the, the aggregation step in the middle, is the message required to be the same for each of those inputs?
Yes, typically threshold signatures and message is the same. It's like multi-signatures, aggregatable signatures, that we just combine things with different messages.
Okay.
So what do we know for threshold signatures? So on top of correctness and comfortability, I'm not going to give you the full definition here, but essentially for comfortability, you want unforgettability against T-1 corrupted users. So as long as you have less than the threshold corrupted users, you shouldn't be able to forge signatures. And the property that is often required in threshold schemes is that of robustness, which basically says that if one of the parties aborts, you want to be able to still complete the property. What do we know for the signature schemes that we've been discussing? In ECDSA, there is actually a very, very long line of work on threshold signatures. There are the most notable techniques among some of these works is that they're doing some pre-processing to reduce the costs of online signing phase. And there have been works that actually have identifiable aborts, so maybe the protocol is not robust, but at least you can identify and potentially penalize the aborting parties. For Schnorr, maybe one of the most notable recent schemes is Frost. We have one round threshold signatures, again with identifiable aborts. And for BLS, we also have a few constructions. Something to note about BLS is that it only allows for static adversaries. The adversary cannot corrupt, as I said before, additional parties throughout the game, which is actually satisfied by ECDSA and Schnorr. So here I would say, in threshold signatures, BLS is doing, maybe a little bit worse in the sense of the security model here. And again, I have this table to kind of summarize the properties that we discussed without, of course, having all the caveats on the security models and so on under the radar.
Is there any idea if that's a fundamental limitation of BLS, or?
I'm not aware of any possibility results, but I'm also not aware of any proof in the adaptive model. That's a good point. And this was actually recently, like a 2020 paper, it's not a very old work. It might be, I might not just not remember. The last two signature schemes that I want to mention, if people are still here with me, are those of ring signatures and adapter signatures, and that will be the end. So, ring signatures have been used in the blockchain setting mainly for privacy oriented cryptocurrencies. So the idea of a ring signature is that you have a signing algorithm that takes as input a message, a secret key, and a so-called ring, which is a set of public keys. The secret key should correspond to one of the public keys in this set. And in the verification, you get the message, the ring and the signature, and it should accept or reject. The important property that you get here, and again I'm not going to formalize things, I'm going to go a little bit faster on those last two signature schemes, is that you actually want anonymity. And what does this mean? This means that when you see a signature, you don't know who was the signer in the ring. Okay, so who was the user that signed. Notice that this is different than threshold signatures because the signing algorithm is not interactive or anything. I'm just signing alone. I can pull the public keys of whoever I want without them being ever involved and create a signature that is hiding my key under their keys. In threshold signatures, people work together. Okay? So you shouldn't view this as like one out of n threshold signature. This is not the case. So I think I'm going to skip the security game here, but I'm happy to discuss it offline with people if you want to. And as I said, the most notable use of linked signatures is in Monero, where they're basically used to hide who was the sender of a transaction within the ring. We have seen additional applications not strictly on like cryptocurrencies, but when they were originally proposed, they were proposed as a way of electronic voting, hiding who you are among a set of voters, and also for whistleblowing, which again might be interesting like layer 2 applications. What do we know in terms of constructions? So ideally, when you construct a ring signature, you want the signature size to be sublinear to the size of the ring. Ideally, you want to avoid any sort of transit setup, and optionally, you might want accountability. You might want to be able to figure out who was the signer. They were introduced in signatures back in 2001, and there is a bunch of sublinear constructions in the random order, CRS, and standard model. Here, unfortunately, there is not a strict mapping to ECDSA, DLS, and Schnorr, as I was doing before. Some of these schemes are under similar computational assumptions, but it's not like we can just convert, for example, BLS to a ring signature. Okay, so there might be schemes that kind of use similar schemes, but it's not like this one-to-one mapping with the properties that we did before. The last thing that I want to mention, just because these kinds of signatures kind of gained some popularity the last couple of years, are the so-called adapter signatures or scriptless scripts. So these are signatures that achieve two properties at once. You're able to authorize a message as a regular signature, and at the same time allow the leakage of a predefined secret value. So what's the idea here? The idea is that this is kind of a very different signature scheme because you have a signer, the secret key and the public key, and you have some entity, some party that it's typically called the publisher that knows some secret and also has a message. So what is the idea? The idea is that if you get a signature from the signer on the message, then this should allow the signer to extract the secret public. So in a very high level, the protocol allows the two parties to interact, send some messages to each other. From those messages, you can view this as some sort of like a pre-signing process. From those messages, the publisher can get a signature using the secret, sorry, so I omitted the message here, the message and those values. And this signature should verify under the message. And if this signature is posted somewhere, typically in a blockchain, from the signature, the signer can actually extract the key. So you might be wondering why this is even useful. This is useful in a sort of fair exchange setting where you might have, I'm just going to go very quickly through this, I'm not going to analyze this, but if you have like a seller that wishes to sell some secret and you want to kind of pre-lock the coins of the buyer before starting the exchange, these signatures kind of allow that very natively. Note that this fair exchange on cryptocurrency like Bitcoin is also possible without these signatures, but then you're really stuck to use the particular hash functions that are supported by the underlying system, while doing it in a signature level might give you a little bit of more flexibility. They were, as a primitive, they were introduced by Poelstra in 2017. We have compatible Schnorr and ECDSA constructions, and unfortunately we have impossibility results for BLS and in general unique signature schemes. So again, the nice thing here is that if your blockchain system supports Schnorr and ECDSA, you can build these adapter signatures where you're not stuck to use a particular hash function in the process. Yes.
And W contains some of the semantic content of M.
I don't think there is any restriction on whether W and M are related or not. So you should view W as something that the seller wants to sell. For example, I don't know, like a digital image, like an NFT or something, right? And first, what I'm doing is I'm going to hash it. I'm going to prove to you that I'm hashing the correct thing, and then use this protocol just to get a fair exchange of coins and
Right.
peanuts.
I was thinking more an application for something like selective disclosure of a certain part of like a credential, right? Where M would be like encrypted and you want to reveal some subfield containing M unencrypted as W.
Right. Exactly. Yeah, you can use it for something. So I'm sorry to keep you longer, and I just want to conclude with some takeaway points. There's literally like a zoo of digital signatures, many schemes with many different properties, and I didn't even cover every single signature scheme that we have seen in the blockchain space out there. All the schemes that I discussed are not post-quantum secure, so there's a lot of discussion on also what can we do with post-quantum secure schemes. We know lattice-based and hash-based signatures. There are efficiency issues or missing features in such schemes. I want to highlight that it's very, very important to understand the security model when you're trying to decide which signature scheme to use. Understand, what attacks is each scheme secure against, under what assumptions. And very, very importantly, also look out for implementation level and API issues. There can be a loophole for vulnerabilities, and we've seen that multiple times in the space. And with that, I want to conclude, and thank you, and sorry for taking long.